X-ray. Ramesh did his graduate work at the University of Bangalore. He was then briefly spent some time in India, but then did a postdoc at Caltech where he really started doing astrophysics. After that, he was for a while a professor at the University of Arizona, and then followed that up with his current position. He's been a professor at Harvard University for many, many years now. Ramesh is, I think, known for doing work on all sorts of things. He's particularly noted as an expert on high energy astrophysics, physics of accretion flows, and today he's going to talk about some applications to black holes.
Thanks, Shane. It's always a pleasure to come here. We all know the world's smartest people are here at CITA. Enjoy talking to everyone. We had some nice conversations with people. Looking forward to more this evening. So I have a talk on this topic. Basically, it's an old topic, as you know. People have been wondering how relativistic jets operate. In particular, where do they get their enormous power? And one of the most popular paradigms has been, one way or the other, it's the spin energy of the underlying black hole. So I'm going to try and persuade you that there is probably some truth to this connection. That's the purpose of my talk today. So it's going to be all about black hole spin and then about relativistic jets as I get towards the end of my talk. The particular black holes I'm going to discuss are stellar mass black holes, little guys with mass in the range 5 to 20 solar masses, very different from the supermassive black holes in galactic nuclei. But we think it's okay. Black hole physics is black hole physics. It should be scale independent. So it doesn't matter which black hole you study. Take the system where you can do the best observations or the best theory, and hopefully you learn some lessons that apply to all black holes. So today's story is on these guys. And the particular black holes that we see and observe and study are the ones that are in interacting binaries. So this is a cartoon of an X-ray binary with a black hole. So this little dot down there is the black hole, companion star. Gas is flowing from the companion star into an accretion disk. And the accretion disk gets very hot, produces X-rays. And sometimes these systems produce relativistic ejections, relativistic jets, very much like we see in supermassive black holes, in quasars and blazars, etc. So those are the jets I'm interested in, and those are the black holes. Now, black holes are particularly interesting as laboratories for high energy astrophysics because they're so simple. As you all know, at least within the classical regime, you can describe a black hole completely with 2 or perhaps 3 numbers. It's got a mass m, it's got an angular momentum j, which we usually represent through a dimensionless number a star, given by this formula, j equals a star gm squared over c. And in principle, it could have an electric charge, but this line is to indicate that we believe that in astrophysics, whatever charge they have is going to be at least dynamically unimportant. They do interesting things in terms of electrodynamics, and perhaps one should revisit this question, but most of us would like to think that for astrophysics, we only need to worry about 2 numbers with a black hole, and I'm going to work in that picture today. Now, this simplicity, we think, should buy us some real deep understanding of black hole systems. Because when you come down to it, if I look at an accreting black hole producing a jet or whatever, how many different things can determine the physics of what's going on? There are the 2 parameters associated with the black hole. There's the mass and there's the spin. Maybe 1 or 2 other external parameters like the mass accretion rate, how quickly you're accreting, the inclination from which you're observing. And there are not many other parameters you can think of. So these are really simple systems. Even though they look so complicated and do such crazy things, ultimately it should all be understandable in terms of a few parameters. And in particular, if you look at the 2 parameters describing the black hole, in my view, M is just a scale. Small black holes, big black hole, you just scale up everything by, all lengths by m, time by m, etc. It's the same phenomenon. This guy, I believe, is the one that's going to have perhaps a much more important qualitative effect on what you observe. Because as you know, you can't take a spinning black hole, the solution, the curve metric of a spinning black hole, and do any simple stretching and make it into a non-spinning guy. Whereas you can always scale up m, up or down. A star is a truly unique fingerprint of what the black hole is doing in its vicinity, and we do expect that A star should have some influence on the most energetic phenomena associated with black holes. So this has actually motivated us at the CFA for the last several years to go and measure these numbers. We have lots of theoretical ideas, but it's time to do some real measurements, measure the two numbers, look at all the phenomena, see if there is any connection between the black hole parameters and what the black hole does. Mass itself is a relatively easy measurement. It's been going on now for a few decades, as you know. And these are binary systems, and binaries are among the best systems for measuring mass. Because you have a companion star, which is going around under the gravitational influence of this black hole, and by observing what that companion does, its velocity, period, etc., with some modeling, you can get a reasonable estimate of the mass. And this is a nearly complete table of all the stellar mass black holes for which masses have been measured. They are not super accurate, as you can see. There are some very good estimates, 6.6, 6.3, 6.9, 14 to 17, but some are pretty bad. Let's just limit 10 to 18, so each system is different, but the point is that we do have some information on their masses, and as I already indicated earlier, the range is from, say, 5 solar masses to 20, which is already an interesting point. I won't dwell on this further. We don't see black holes below about 5, and we don't see neutron stars above about 2. So there is a little hole there, a pretty deep hole. If you plot distributions, there's this neutron star thing that just dives at 2, and then the black holes come up at 5. And what happened to the guys in between is a little bit uncertain at the moment. There's probably some bifurcation in evolution. To go the neutron star route, of course, you have to end up in a mass less than the maximum neutron star. Presumably, when you go the black hole route, something takes you not to the boundary, but here to 5 and beyond. Anyway, that's not the topic of today's talk. Today's talk is all about spin. And so the question is, how do you go and measure the spin of a black hole? I'm going to talk about this method, X-ray continuum spectrum method, which I'm sure you've all heard from Shane. He's one of the, I don't want to say unsung, some hero of this field, yeah. He's made a major contribution. I won't say in details, but I'll mention it as I go along. This is the one I'm going to talk about. There's a second method based on broad ion line emission from X-ray sources. It was really developed for AGN, has been applied to X-ray binaries with, I would say, mixed success, and I will really not say much about this. There is a method in weighting. Question mark is to say that it hasn't really been established. Some people think one of these days we will start using these periodic oscillations, quasi-periodic oscillations to measure spin. I won't say anything about this. This, I've probably said already everything, but I might have one slide. This is the one I'm going to focus on. The work has been actually done by Jeff McClintock and myself now for more years than I'd like to think. I think we started in 2005 or so, 7 years. It's been hard work, but I think it's slowly beginning to pay off. A whole lot of people have helped us. This is in alphabetical order, but Shane is right there in front. And the highlighted names are the ones, the younger people who really made the thing work. Lots of students, postdocs, and of course, senior people like Ron, Marguerite, etc. So how does the method work? So I'm going to just give you the outline of the method. I won't go into too many details. It finally comes down to the fact that in general relativity, there is this concept of the innermost stable circular orbit of ISCO. I'm sure you all know this, but let me just remind you. So if you work in general relativity, and you put a test particle around the gravitating compact mass, let's say it's a black hole, you put a test particle and try to set up a circular orbit, you can do this fine at large radii. In fact, those orbits will look just like the Newtonian circular orbit, which we all know how to compute. But as you bring the test particle closer and closer to the center, these orbits start deviating from the Newtonian orbit solution in the sense that the velocity will be different, the period will be different, etc. slightly, until you come to a radius which is the last stable circular orbit. By which I mean, if you took a test particle inside of this radius, whatever velocity you give it, it will not go into a circular orbit. Or rather, it will not go into a stable circular orbit. You can try and put a circular orbit, but it will be so unstable that if you just tickle it slightly, either it will go up to infinity or come to the center or do something crazy. This is not true in Newtonian physics, as you know. With a point mass, you can put a circular orbit wherever you want. However, in Newtonian physics, you also know if you just followed Newton, took a point mass and put a test particle very close to the center, you'll get a solution, no doubt. But the velocity of your particle will be greater than the speed of light. The closer in you come, the faster it goes, and you know immediately Newton doesn't work. GR tells you how you should do the problem relativistically, and one of the effects is there is this innermost stable circular orbit. The position of this ISCO is 6m, which is just shorthand for 6gm over c squared, for a non-spinning black hole. But once you have a spinning black hole, that radius is at a different location. And this picture shows you how it varies. So this shows the radius of the ISCO in units of gm over c squared as a function of the spin parameter, non-rotating black hole to the maximally rotating black hole. There is this nice, smooth, monotonic line, just comes from theory, just using the curve metric. It is at 6m for a non-spinning black hole, comes all the way down to 1m for the maximally spinning black hole. It's monotonic, so if you had any method that can measure this quantity, r over m, r is over m, you would just read off from this diagram what the spin is. So suppose I had a system where it was 3, I would say, the spin must be 0.7, 0.78 or something. If it turns out to be 1, I'll say the spin is 1. If it's 6, I'll say the spin is 0, and so on. This is not an absolutely straight line. It's got all this curvature. And one of the things that does is that there's a little bit of nonlinearity in the way you map from this measurement to this axis. And this is illustrated in this slide. So I'm imagining that I'm measuring the radius of the ISCO with some fractional error. I think it's 10% error or something. If I measure 6 plus minus 10%, I will get a spin of 0 plus minus a fairly large error, maybe as much as 0.2. But if I measure a radius close to 1, even though I may have the same 10% error in this axis, I will still get a very, very precise spin. In fact, the spin will be practically 1. This curvature guarantees that as I go towards most rapidly spinning black holes, even a pretty crude measurement of this quantity will give me a pretty good measurement of the spin. So you just keep this in mind when we look at some numbers later on. You will generally find that error bars are larger when we are close to 0, much smaller as you approach 1. And this is the reason for that. Because what you're measuring is this quantity, R is over there. How are we able to measure this? Yeah?
When you have the negative spin on that, so if you keep this going the other way, do you ever see that?
This is a very interesting point. We have now got measurements of 10 black holes with spin. We haven't yet found a guy with negative spin. We could, that is to say, our analysis will allow us to go to R ISCOs above 6. We can go up to 9. 9 is the maximum allowed. We have never seen one yet. They're all between 6 and 1. It's telling us something.
So that's just the equation spinning up with that
Absolutely. I mean, it's not just accretion. Even without the accretion, we do expect the black holes to be, in the same direction as the binary and the same direction as the accretion. It's perfectly natural. But I take great pleasure from this result in the following sense. We have a lot of people who think that we're doing crap. They think that we are just producing random numbers. And I say, if I got random numbers, which can be anywhere between 1 and 9, how come they're all below 6? Which is where I expect to see. So in that sense, it's really very nice that by the time you make a big sample, you're still not seeing any of these guys down here. We have now come to the point where if we did find one negative, we would actually believe it. And we would now, start thinking, why would this one system have a counter-rotating disk?
I would say you're doing even better because they could be more than 9 or less than 1. I mean, you wouldn't be able to.
Absolutely, yeah, sure. Shane is absolutely right. The model itself will only allow from 1 to 9. But the data might have demanded 16. And what would happen is we try to fit that data with whatever model we use. The model will push this parameter up to 9, and it will say that I still have a very poor fit. I want to go beyond 9. And the chi-square will tell you. So yeah, we have never had any problems there. We always seem to be sitting down here, producing spins between 0. Yeah.
And does ISCO depend on the inclination angle of the orbit?
Yes, you're absolutely right. We are assuming that the accretion disk is in the equatorial plane with respect to the spin axis. And this is reasonable. The disk will get aligned with the spin through various interactions. But we are not assuming that the whole system is oriented in any special direction. Each system has its own orientation, which we try to measure and use in the analysis. So the viewing angle can be anything, but as far as the internal geometry of the object is concerned, the disk is taken to be in the equatorial plane, and this curve corresponds to those equatorial orbits. The moment you go off the equator, you start getting precession. So you won't have a fixed orbit. It will start precessing. In fact, that precession is the reason why it finally will align with the equatorial plane. Okay. So how do we think we can measure ISCO? This is, yeah.
Before we go on, so if you have one of these counter-rotating, would it stay in that plane, or would it flip by the time of that?
This people have thought about. And I think if you put it exactly at 180 degrees, it will stay there. I think if you start tilting it, and you wait long enough, because this interaction, which is length steering precession and other viscosity, etc., comes in, I think there is a certain orientation beyond which the thing will flip over altogether. Whether these systems will have the time to do that, I don't know. But as I said earlier, we don't expect to see counter-rotating disks. The physics of these binaries is such that probably they are all spinning in the same sense as the orbit, and the disk will be in the same sense. This is the natural state of affairs. Yeah. Okay. So this is the picture that one should have of what an accretion disk might look like if you could see it in the idealized case. So you've got gas flowing in, accreting, getting hot, and in fact it's hottest near the center. So the central region will be the brightest. And as you know, an accretion disk is essentially parcels of gas which are for all practical purposes going in circular orbits, slowly spiraling in. The net radial velocity is much smaller than the tangential velocity. So it's just a sequence of circular orbits. The guy comes slowly down, 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 until the gas hits the ISCO, and suddenly there are no circular orbits left, stable orbits. So when the gas crosses this radius, since there is no stable orbit, it will just fall into the black hole. That will be a dynamical process. This whole process is slow, viscosity-driven accretion, and then a dynamical fall into the black hole. And therefore, it's natural to expect that there will be very little radiation inside the ISCO because everything is going too fast. There will be radiation outside the ISCO because that is in the viscous region. And in fact, the bulk of the radiation will be just outside this, within a factor of 2 or 3 of this. So that's the picture, okay? And if you now compare a non-spinning black hole and a rapidly spinning black hole, what the previous plot indicates is that the size of this dark region will be larger in the case of a non-spinning black hole, smaller in the case of the spinning black hole. Correspondingly, this bright region will have a larger area in the non-spinning case, will have a smaller area in the spinning case. So it's just this curve, how the ISCO changes. So our method is essentially a way of using data to estimate the radius of this dark region. And then once you've measured that, compare it to M and you've got your spin measure. Okay, so how can we do this? Well, firstly, we don't have such nice images of accretion disks on black holes. They're very, very small. Okay? An artist can draw this, but our telescopes cannot actually capture it from a real object. So we actually do this in an indirect way. And this is an indirect way that everybody has seen long, long ago when you first heard about how you measure the radius of a star. Right? A star, if you think of it as a black body source, its luminosity is related to the flux you receive by just the inverse square law, 4 pi distance squared times f. But the luminosity is also the area of the star multiplied by sigma t to the 4, where t is the temperature of the radiation. And from this you get this nice little relation which says the solid angle of a star is pi f divided by sigma t to the 4. F is the flux with a bolometer that I measured here on Earth. T is the temperature I get from a spectrometer which is fitting the spectrum. E is the observables. I get the solid angle directly. If I also knew the distance to the star, then I'm in business. I can solve for the radius. Ultimately, the point here is if I know the luminosity of the object, the smaller I make the object, the hotter it has to be to put out that much luminosity, right? Because of the sigma t to the 4. And this is all there is to it. You measure luminosity, you look at the temperature. If you get a very hot temperature, you say the area has to be small because I know how much luminosity. If it is cooler spectrum, area has to be large. And once you know the area, then you get the radius and you get the spin. That's all we are doing here. Here is my, pictorial representation of what the disk is. It's producing X-rays, mostly from this region. I measure the flux in X-rays, the temperature by looking at the spectrum. I assume that it's black body or a certain kind of modified black body that Shane has told us how to model. From these I get effectively the solid angle of the bright region. Then I go and independently measure the distance. I need to know the inclination because there are additional geometrical factors. Whether I'm edge on or face on, these are all things we can do. So at the end of the day, I get an estimate of the radius of the ISCO by doing all the modeling. I meanwhile independently measure the mass and I get this. Okay, so that's the idea. So you can ask, it all looks very good. Qualitatively, the idea is good. Can you actually make this work? First thing is you would notice it's not enough to just have X-ray data. We need to know the distance to the object. We need to know the inclination of the disk. And we need to know the mass of the black hole. And all of these have to be measured with reasonable precision. Because even though, our ISCO changes by quite a bit between non-spinning and spinning, still only it's a factor of a few. We cannot afford very large errors in any of these things. Fortunately, it turns out that it is possible to measure these three quantities independently with sufficient precision. We keep trying to do better, but it can be done now already to provide useful results. Second point, this whole business works only if the emission is like black body. Ideally, it should be a perfect black body. But if it's not a perfect black body, it should at least be modelable in some way. The deviations we should be able to understand from first principles. And for this, we have the following fortunate circumstance that most of our systems go into, they do crazy things at different times. There are times when they go into a spectral state that you have no hope of modeling at all. It's just much too complicated. But every now and then they get into a good mood and they go into this so-called thermal state, where for all practical purposes it's nice, relatively cool, optically thick gas, radiating like a black body. Not exactly a black body, there is modification, just like even for a star. No star is a perfect black body. But we know how to do stellar atmospheres and we know how to do the modeling. So Shane is the world expert on how to do the modeling for our accretion disk spectra. And because of that, these deviations from black body are under control. So just to give an illustration, so this is actually from one of Shane's papers. This is the X-ray data. This is EFE, like nu F nu, versus photon energy from this particular guy, LMCX3. That's what it looks like. So there's a nice, smooth bump, which we say is this black body-like radiation from a cool, thin disk. There is some extra stuff out here at much harder energies. This is the stuff that we really don't know how to model. But we think it's some kind of a power law. You just model it and throw it away. Okay? And that is okay because this is so weak compared to everything else. Whatever you do here is not going to affect how you model this dominant component. So that's really the key. The key is the bulk of the emission, more than 90% of the emission is in a component that we think we can model. There is junk, but fortunately it's weak, so it doesn't matter what you do to it. So I think in this case, this was Shane's model, some compromised something, he just threw it away and he fitted the rest. So to fit the rest, you basically need three parameters. You need to allow for interstellar absorption of the softest energies. That is through a column, one number. Then the other two parameters which we want, the flux and the temperature. Flux is essentially the vertical position of this curve, and the temperature is the horizontal position of this curve. Essentially what you want to know is, where is this peak, how high is the peak, and at what keV is the peak coming. That gives us these two numbers, and I would claim, if you've got data like this, and you've got a model that's as simple as this, you can't really get this wrong, okay? You could get it wrong, of course, if your non-black body effects are all modeled very poorly, but we trust in Shane. We think it's all done perfectly, yeah, right? After all, you guys hired him, right? It has to be right. So, so I think it's all fine. And we, in fact, have been using Shane's model for years.
Well, just a quick question.
Yeah.
This disk you're modeling is radiation dominant.
Just a little bit radiation.
Okay. Because my question was, well, the background state, is it actually self-consistent? Is it a worry about how this cures the most stability?
You know, Chris, that's a really interesting question. But we say, we don't care. This disk is not unstable. Look at it, right? It's certainly not becoming violently unstable, producing corona. So one way or other, nature has managed to produce a black
If
body.
it's not very radiation dominant, it's probably not much of it.
This particular one, okay.
Yeah, yeah. It's again, I won't go into the details, but we typically look at systems like 10 or 20% eddy. You don't have too much trouble yet from the light and early instability. The 10-20% is also, we think, the region where these models are particularly, effective. Scale height is very small. It's a truly thin disk, etc. Yeah. So yeah, there is a sweet spot where we think all of our assumptions are okay.
But for the fastest spins, it's not obvious.
It's not obvious, and in the fastest spins is where these atmosphere models give the largest trouble. But fortunately, that is where we can afford a large error and still get a pretty good spin. So what can I say? It all kind of works out at the end. Now the real question is this model, right? So we say that we get radiation from this region here, and somehow we can model it well enough to decide where the inner edge is. this, of course, is the weak point in any such method. How good is your model? One good news is this model doesn't really care very much about this alpha parameter. Standard disk alpha doesn't matter because we're just measuring radiation produced by gas falling in a gravitational well. It's really just energy conservation. So the shape of this luminosity profile, we think, is rather robustly determined just from converting gravitational energy to radiation. And there's an old model, Novikov and Thorne, which tells you exactly how this profile is supposed to. This is some measure of luminosity versus radius. If you have a non-spinning black hole, this is what it will do. It will cut off at 6m, that's the ISCO. If you have a rapidly spinning black hole, this is what it will do. It will cut off somewhere here. This is the ISCO of this black hole. And the only point to note is that the peak of the emission moves in as I make the spin faster and faster. So the region that's radiating gets smaller. So therefore, if I have a given luminosity, the spectrum has to be hotter. And therefore, by looking at the spectrum, I can tell you how far in the disk has gone, and I can get the spin. That's the idea. And so long as you believe these curves, it should work. But should you believe these curves? This has been an issue that's been around now for several years. The issue is all related to this business of the luminosity going to zero at the ISCO. Why should it go to zero at the ISCO? Well, Novikov and Thorne, following Shakura and Sunyaya, just made an answer. They said, look, this is where the gas is going from viscously driven to dynamical infall. So there cannot be any stress at the ISCO. And if there is no stress there, then there won't be any dissipation, there will be no luminosity. So they just put this as a boundary condition. And once you put the boundary condition, the rest of it follows. Okay? This is all just energy conservation, but there is a boundary condition that you put in by hand. And Krolik and others questioned this boundary condition. And it's not like this. Started, even I think Novikov and Thorne knew, this is a questionable assumption, especially if you've got magnetic fields. And we believe disks are driven through MRI, which is a magnetic phenomenon. And so there would be magnetic fields, especially magnetic fields threading through the ISCO, from the disk into the plunging region. And so it's like ropes. So there are these ropes which are stretched across the ISCO, which are pulling on each other. That's the stress. So how can the stress be zero? If there is any field line going from here to there, there's going to be a non-zero stress. How important is it? Right? This is the question. And the only way to really answer this is by doing a serious simulation with the full MRI, MHD, in general relativity, a full GRMH simulation. Still fixed metric. People here who do the real problem with varying metric, we are still, little kids in this business. So we have a fixed metric, but we put this magnetized disk. And one of the things we did, I would say it was an innovation, when we started this, was to make our disk really thin, geometrically thin. Because we had a number of reasons for thinking that geometrically thin disks can really behave quite differently from very geometrically thick disks. And all the previous work had been on thick disks. And all the intuition had been on thick disks. So we made really thin disks, which over an R of order 0.05. And some others have also done. At Noble and company have done quite a few simulations similar to this, and so have we. So let me just very quickly run through the results we got. The first thing we wanted to ask was, okay, let us concede that the stress is not going to be zero at the ISCO. What will it do to the dynamics of the gas? According to Novikov and Thorne, there is a viscosity which is constantly removing angular momentum. This is angular momentum measured as the gas comes closer and closer to the ISCO. And once it crosses the ISCO, there is no stress. Angular momentum will be constant. Clearly, the simulation is not constant. So there is something going on even inside the ISCO. There is a slight decrease. But please note, zero is way down here somewhere. This is not a major deviation. In fact, it's surprisingly close to the idealized model. So what we take from this is that there may be a stress. It may even look like a large stress. some measures, it looks terribly large. But finally, what counts? You just ask, what is it doing to the gas? It's not doing anything very much. It's pretty much doing what the simple model predicted. This, of course, is not what we measure. What we look at is the luminosity. So you can ask, what does the luminosity do? So this is what the luminosity does for different values of spin. Luminosity versus radius. And in each case, the dotted line is what Novikov and Thorne predicted. It goes exactly to 0 at ISCO, and there is 0 luminosity inside the ISCO. The real truth is, it doesn't go to 0. There is some luminosity inside, non-zero, but it's clearly rather small. It's only a few % of the total. So that's again rather encouraging. It means that, of course, we will make few % error, but it's not like order unity error. This is, it looks like a relatively weak effect.
Well, but the radius is smaller, so that affects temperature.
Absolutely, it affects the temperature.
Correction is larger.
Absolutely. So one has to do the next step, which I'll show you. There are quantities that are quite different, however. I just showed one picture here. Surface density of the gas. This is what Novikov and Thorne predict. This is what the simulation does. It's completely different. Their model, because of their boundary condition, does pretty weird things right here at the ISCO. In fact, if you did this in a very simple-minded way, then actually you go to infinity. But then there's something else that corrects it. But the point is, some quantities can be quite different, but the things that matter for us apparently are not that serious.
And so the surface density doesn't matter because the disk is optically
thick. However, here it's becoming optically thin. What's called effectively optically thin. And that has a real effect on the spectrum. So I think thank you for the question. Out here, whether the density is doing that or that, it's still pretty much an optically thick gas. And all you care about is how much luminosity comes out. The exact surface density, whether it's infinity or there's optical density, 100 or 1,000, it doesn't make such a big difference. In here, as you go closer and closer to the black hole, you're getting thinner and thinner because you're plunging in. Then the optical depth starts becoming an issue, and it's definitely not black body. Deviations are quite large. So in fact, this picture shows what happens. So one particular model, if you look at the spectrum from large radii, they look pretty much like the spectra you would have predicted without going through all of this hard work. But the moment you go inside the ISCO, these blue curves, your temperature becomes much larger than you think. Getting optically thin becomes very, very hot. And in fact, we think some of this radiation may even be contributing to this power law. The power law, which I said nobody understands. Still true, nobody understands, but maybe some of that power law one day we will understand. As this is just hope. We don't know. But the point is, even this little emission here, to a large extent, is probably not going to affect us because it's coming out in the power law. Okay?
So this luminosity that's being emitted from the equation disk, or the luminosity that makes it to infinity? How much of this?
Oh, this is everything plotted here is what reaches infinity. That's all that they're looking at. Okay. How am I doing for time? I want to keep time for relativistic checks.
20 minutes.
20 minutes, okay. So I gave you all the theoretical reasons why we think this method is pretty good. And if we have looked at it with the theorist's eyes to see where are the things, what are the things that can go wrong. We've done these heavy-duty simulations, and so far there is no showstopper. It looks like we are in a happy situation where basic ideas developed so many years ago are a pretty good first guess of what goes on, and then you can do better. You can do better than black body, you can do better than Novikov, but they're all, smaller effects as you go on. Does it actually work in practice? I'll show you a couple of tests we have done, which really indicate that this thing is very solid. Basically, I'm going to show you one object which has been observed like 1,000 times, okay? You have let's say several hundred observations of this object are available. They've been done over 30 years with many, many different satellites, X-ray satellites, when the source was doing various different things. And you can look at all of this data, analyze each of it independently, not as a single problem, each of them independently, and ask, what is the spin? What is the spin? What is the spin? Or more accurately, what is the ISCO? So here is all the data. Okay, this is LMCX3, the same source that I had shown earlier. The data there was Beposat. It's probably this one. Shane will know which one it is. One of these Beposat data. So this object is something that's been shining ever since the dawn of X-ray astronomy and has been observed everywhere. And there are all these data from, there are actually more satellites than we only looked at 7 or 8 of them. So much data shown as a function of time, 1980 to 2010. Luminosity in Eddington units, it goes up and down, there's various things. We look at all the data that lie in a certain range of luminosity. This is the range where we think the model should really work. Between 5 and 30% of the. It leaves us with 403 spectra. So you got 403 spectra here. And you go and model each one of these observations independently. You fit for NH, flux, temperature, do our modeling, calculate what is the radius of the ISCO. This panel shows you the radius of the ISCO that we derived from 403 independent measurements. And you know, that's about as consistent as you could ask for. This is the whole range from 1 to 6. Okay? We can measure our ISCO to phenomenal accuracy. In fact, the only thing that kills us is all the other systematic errors. Clearly, you can get a really good measurement from these data. Here's another object, 1550. In this case, about 60 spectra. The X's are the best spectra. The triangles are the so-so spectra. We were really encouraged that the so-so spectra are almost as good as the really good spectra. They all give a very consistent answer. This particular object, just as an aside, it turns out that you can also measure its spin using this relativistic iron line. It's the only object that we have studied where we can get a spin from continuum fitting and collaborating with the iron line guys. They are able to get a spin for the same object, and they are consistent within their measurement uncertainties. This has not been done for any other object. Okay? And there are, in fact, objects where the two measurements disagree a lot. I won't say more for that. Okay? Well, this is just to show you that we don't always have data like this. Once in a while, we come up against an object for which there's only one spectrum. This is this very famous object, A0620. This is the granddaddy of them all. And it's really an important object. This is where the whole black hole stellar mass game started. This fellow had what's called an outburst in 1975. And there was one spectrum collected by this old satellite, OSO 8, in 1975. And this guy has been quiet ever since. It has never done anything since then. That's all the data we have. But it actually turns out to be a really good thermal spectrum. And so we can get spin, and we actually believe it quite well, because this fellow is close to being one of these ideal systems with a very well-behaved thermal spectrum. There is a caveat. Let me just skip past it for the obligated checks. Okay? Ask me a question about this data. These are all the results as of now. 9 systems. This is Shane's measurement, LMCX3. The rest are all from our group, and I think Shane is probably on most of those papers. And we get spins. Okay, I already mentioned, right? So these are the spin values we get. From close to 0 up to close to 1. We could have got negative values. We haven't got any negatives. That's rather nice. And the error bars, these are our best guess for all the errors. Most of the errors are dominated by errors in distance, mass, etc. Some of these errors in parentheses are where we have taken published errors and doubled them. So these were very early in the game. These were measured in 2006. We haven't gone back to them since then. I think today we will give them larger errors than we did when we first started this work. But anyway, that gives you an idea. The nice thing is we get the whole range from 0 to 1. So as far as astrophysics is concerned, if spin has any effect on observational phenomena, we have a nice sample of objects that span the whole range. We should be able to see. This is where the relativistic jets come. Because we can now ask, does this spin have anything to do with relativistic jets? In fact, there's a whole big enterprise here, not only relativistic jets. We imagine the spin will have some effect on these various spectral states, how black holes vary in quasi-periodic oscillations, etc. This is the only place where we have made a little start right now. I'm going to show you what we have got on this result. Relativistic jets versus black holes. I don't need to show you pretty pictures of relativistic jets. These Cygnus A, M87, some random radio galaxy. These are these powerful ejections which come out with large Lorentz factors from a central supermassive black hole, and they've been known for many decades. These are all supermassive black holes. A great breakthrough in 1994 happened when Narayan and Rodriguez found relativistic jets in stellar mass black holes. So this is the most famous of them all, GRS 1915, 105 microquasar. And this is their discovery paper. I'm sure everybody has seen this. Essentially, radio images of this object as a function of time. And what you see are blobs moving away from the central object at a pretty rapid speed. So in fact, from the rate at which these blobs are moving, you can estimate the velocity. And it turns out that the Lorentz factor is 2.6, the velocity is 0.92c. So this is a beautiful analog of these guys, except that this is now in our galaxy, stellar mass. And since this object, other objects have also shown this kind of blobs moving relativistically and other kinds of radio emission. So now the question is, where does the power for this jet come from? Right? This is the question that I started. People would like to think that it is coming from the spin energy of the black hole. For a spinning black hole, by some means, almost certainly involving magnetic fields, some of that energy is being tapped and comes out as a relativistic jet. However, there is a counter model, which is it says simply that you've got accretion. There's all this luminosity and huge amount of energy involved. Why can't we just tap a little bit of that energy and make the jet from the accretion? How would you compare the two models? In this model, you expect the power in the jet to be some function of the mass accretion rate. Whereas if the spin of the black hole is involved, you would expect the power in the jet to still depend on m dot, because that's finally the energy scale for everything. But there should be an extra, hopefully large dependence on A star. So if we could somehow compare different systems, try to catch them at a similar value of m dot, a similar value of L over Ln, and have a range of spins, see what the jet is doing. Doesn't show any dependence on A star. Okay, the simplest thing you could have thought of, this is what we first thought of, was maybe we will find that only the guys with the large spin produce jets, and the guys with small spins do not produce jets. And for us, jet means radio emission. You see radio emission, it's a jet. You don't see radio emission, it's not a jet. All these R's indicate objects from which radio has been seen. That's not looking very good. You see an R pretty much all the way through the table. Only 3 systems out of the 9 have not shown radio emission. LMCX3 and 30X7 and LMCX1, and you can almost explain why they don't show. Firstly, they're all sitting in external galaxies. There's only 3, in fact, in external galaxies. They're just very far away. It's harder to see the radio. But there's another reason which I'll come to in a second. There also needs some persistent sources. So what we did recently was to go and do this carefully. Okay? Recognize the fact that these are not all identical objects. Even though it's a small sample, there are still subsamples to worry about. Look at the right subsamples. Try to pick a standard candle so that we can look at things at a constant L over L. So the best you can see if there is some signal there. So the first thing to note is X-ray binaries come in two broad classes, black hole X-ray binaries. There are the so-called persistent sources, which shine all the time. These typically have massive companions, accretions from the wind from the companion star. They are persistent, which means they are always shining. Many of these objects do not have jets. 3 non-jet guys are all of this category. Cygnus X1 is also, this belongs to this class, but it turns out that Cygnus X1 does produce radiations. And we can go into why that's different. But that's not my talk. The other guys are what are called transient systems. They all have low mass companions, which is on the order of the solar mass, Rho-Slope overflow, and they are transients. That is to say, these are not systems that are shining all the time, but most of the time they're not shining at all, extremely quiescent. And then once in a while, suddenly they wake up and become exceedingly bright. So A0620 in 1975 did this. Nobody even knew that this object existed before that. Suddenly one day it became very bright in X-rays, and X-ray satellites of those days started looking. They were very bright, practically to Eddington, declined over a period of a few months. Then it died, and it has remained dead since 1975, the last 35 years. Where it went very bright, it also went bright in radio. So there was a big flare in X-ray, but there was also a big flare in radio. And that was caught, fortunately, by the radio telescopes at that time. This is a special kind of a jet. This is what is called a ballistic jet. This is the time when the thing seems to throw out blobs of material and then go relativistically away from the object. So here are a few other objects which did similar things. Bright objects. Since these ejections come right near the peak, we like to think that these are like standard candles. They are roughly close to Eddington within a factor of 2 or 3. And so this scaling, the m dot, if you catch any system near the peak of this outburst, probably their m dots in Eddington units are not very different. So we can look at just that radio emission, look for a dependence in the function of A star. That was the thing. Okay? Good. We have 5 systems that are transients out of the 9. 4 of them are persistent, we threw them away. Unfortunately, one of the 5 was not observed properly in the radio. Really sad. This is a southern source. It had to be done in Australia. Those kinds of things. So they just didn't get the radio data, so unfortunately we are down to 4 objects. Fortunately, they span the range of spins from 0 to 1. The 4 objects, they've got data, good data in radio, so we can measure the radio flux. They all have distances, so we can correct for the distance, we can correct for various things. I'll just show you what the data is. So these 4 objects, if you plot their radio power, suitably scaled, and call that the jet power, and you plot them against the inferred spin that we have got from our continuum method, we get what looks like a nice scaling in a log-log plot. This is a log-log plot, okay? The range of powers we are talking about here is more than 2 orders of magnitude, almost 3 orders of magnitude in radio power. And the spin is changing, of course, all the way from 0 to 1. And the line here is the line that Bamford and Znaev would have drawn. They said jet power should go like A squared, and this is just an A squared line. Look, they didn't know where to couple it. We just put it through the points I by I. Okay?
And this again is all the same LX over LI.
All I can tell you is all of these guys were observed during a transient outburst. And if you believe that during a transient outburst they all go near Eddington, then we think they're same LX over LI. They may differ by a factor of 3. But we're looking at 300 here, so hopefully that factor of 3 is not serious. Okay? So that's the only reason for believing this, the fact that you've got a big range. And the error bars are the best we can do. These are our, you will notice the error bars are tiny for rapidly spinning guys, large for slowly spinning guys, for the reason I explained. Okay, 4 objects. I won't talk about the second plot, but this is, I think, I wanted to mention this. This is the first time anybody has ever produced any evidence to suggest that black hole spin has some astrophysical effect. It's only suggestion, okay? These 4 points you don't want to be too strong, but it is rather intriguing that there is this correlation, and even the slope looks like what the theory might have done. Caveats. What we are plotting is radio power at some selected frequency, 5 gigahertz. That's where a lot of the data is available. Who knows whether that is really a good measure of jet power? What actually comes on hertz per second from the black hole? We think there should be a correlation between the two. A more powerful jet probably will produce more radio. Is it a simple one-to-one correspondence? Who knows? This is what we have. This is what we can observe. So you just plot what you can observe and hope that it's a good measure of jet power. We have only considered these ballistic jets. These jets, in fact, Chris's question is relevant here. These jets come out when Lx over Ln is roughly constant. There is another kind of jet, so-called steady jets. They come over a wide range of X-ray luminosity. So you have to go and make a correction. You need a model. We haven't touched those guys here. And I hope one of these days we will figure out how to handle these guys. But you have to make an LX rescale to study these ones. And Fender has actually done that, and he claims that these jets do not have any spin defect. I don't know.
Does he find that L radio or LX is fairly constant?
No, he's got a correlation which says L radio goes like some power of LX.
It's self-absorption effects and stuff.
It's more than all that. Yeah, there's stuff there that goes into that.
There's an empirical correlation.
There's an empirical correlation for sure, and there's a theory which predicts that empirical correlation, and then you can use that to remove the LX dependence. It's a little too complicated for my taste. I like looking at the ballistic jets because we're not doing any modeling. You just look at data versus data, more or less. This plot is really data versus data. Of course, this data is through our spin deductions, but this is really data. We haven't done anything. Yep. Okay. Then of course there's 4 sources. Can it be just a fluke? So let me give you a little bit of good news. We have a 5th source. There's another guy, a transient source called H1743. And after Jeff and I finished this paper, he with Jack Stein, graduate student, wrote this paper where they managed to produce a spin estimate for this transit, H1743 minus This is not exactly the same continuum method that we have used for the other matter. There is some extra stuff that goes in here. I won't go into the details. I should probably get Jack to come and tell you about it. But they got a spin of 0.2 plus minus 0.3. This is a transient black hole. And when it went out into outburst, it did produce ballistic jets. Unfortunately, when this guy did its thing, somebody was observing the radio, and we know the radio flux. So we can now take this 5th guy and put it in our plot. Yes. So this is H1743. 0.2 plus minus 0.3 is the spin. This is the jet power. Again, this is just an observed quantity, okay? And the line here is the same line that I drew before. The previous line was drawn with these 4 points in mind, and now we put the 5th point, and I say that it is sitting where it should sit. It didn't sit here, or here or whatever, sitting. And this other representation, which I didn't explain, it sits right here as well. So I would say 5 is better than 4, especially when you already made a story with 4 and you add the 5th and it sits where you would like it to sit. That's rather encouraging. This plot is a little bit distracting because of the huge error bars. So Jack actually came up with a nicer way of representing the results. And the point is, we are not measuring spin. We are measuring R ISCO. Our errors are all really on R ISCO. And it's the nonlinearity between R ISCO and spin that makes that plot look so crazy. So he said, let me just plot versus R ISCO. So this is log jet power. This is log R ISCO, which maps to spin through this, whatever the mapping may be. And now what you'll find is because we are plotting it versus log R ISCO, the error bars are relatively similar. And the same 5 points are now plotted in this plot. So here are our 5 points. This is the A squared Blanford-Knight scaling. It looks pretty good.
Well, I think to be fair, what you say is that the points are consistent.
Yeah, that's about all you can say.
But while the power is well measured, all the spins are essentially just zero, right? So in principle, they could be, real values of A that would imply very, very different jet powers.
Sure. I'm not really claiming that E squared is the answer. But I think I would still say it's a pretty strong indication that low spin gives low jet power and high spin gives high jet power. You will again say it's only 5 objects. Look, 5 is better than 4, that's all I can say. Okay? And
well, you have clear evidence for a bi-modality.
yeah, okay. If that's all you grant us, fine. Okay, I'll take that. I'll take that. The low spin guys are low jet power, high spin guys are high jet power. Okay, good. It goes in the right sense. It could have been this way, right? Then we would all have been shocked because we expected a correlation in this direction. This is about all we can say right now, okay? And this is better than we could have said a few years ago, 5 or 6 months ago. So, early days. So let's now explore, the way I see it is the following. There were many reasons why this plot could have been totally garbage. First, maybe Blanford and Knight were wrong, right? Maybe spin and jet have nothing to do with each other, in which case there's no reason for points to plot like this. But there's also, remember, there are lots of things that went into each of these axes. This is really jet radio power. Maybe radio power not related to real jet power. That could have scrambled the correlation. And of course, we might have screwed up in our measurements of A star. All these things could have gone wrong, but they didn't. We still ended up with this correlation. And so I would say it looks as if none of these statements is true. That is to say, jet power probably does have something to do with black hole spin. Our black hole spin measurements probably are reasonably good. And radio power seems to be correlated in some fashion with jet power. Whether it's linear or square root, I don't know. But something. All of these things have to be false for us to see a correlation like this. And that's about all I can say as of today. Let me, yes, certainly went beyond my 410. So this is where we are. We have black hole masses, which I'm sure you all heard about for many years. Spins, we are doing it finally. We are beginning to believe our own measurements. And we are rather encouraged by the fact that when we do the thing carefully, with good data control, there seems to be some relation between the spin of a black hole and the power of the jets that it produces. We have a long list of other things we would like to look at, because we think black hole spin must have effect on many other properties of what we observe. And we'll have to stay tuned for that. And also I still believe that the no-hair theorem, the fact that black holes are so simple, really allows us to transfer any insights we get from stellar mass black holes to supermassive black holes. And so, I think this is fruitful. It's not just for X-ray binaries. Hopefully these lessons will then carry on, maybe to GRBs, but certainly to EGN and laser and other such objects. So I think we'll stop there. Thank you.
We've got a lot of questions, but maybe one or two quick questions.
Is there a survey going on? Like, what's the prospects for finding more sources to use?
This is a hard one. Okay. There are X-ray satellites flying which catch every new transient that goes off. Because half the game is just finding these objects. So long as we have all sky monitors in the sky, and I don't know how much longer we'll have, if X-ray astronomy keeps going, we'll keep finding more and more of these objects. Then once you've found a guy, it's, you have to be lucky enough to catch it in this black body state and get the X-ray data. And then there's this whole lot of ground observations you have to do to measure the mass, to measure the distance, inclination. So a lot of work that goes in. So each is a many-year project. Okay? So we have now come up to 10. We'll probably do another 2 or 3 with what's available. And some of these will get better. So we're trying to improve those as well. But it's not like they're going to end up with 50 objects anytime soon. Okay? A lot of luck if they go to 20 objects. There are many new objects discovered. That's really all we can hope for. So that's why it's already a good time to start looking for these correlations. We didn't want to do this when we had 4 objects. 10 is kind of comfort level, mainly because we'll never have more than 20. Yeah. So that's actually bad news, but that's, we have to do what we can.
Last question.
Any information about that music aligned jet? You didn't have time to look.
There is one of the objects, TROJ 1655. What we know is that there is a certain inclination for the binary that we can measure by looking at the light curve and things like that. And then independently you can measure the inclination of the jet by doing the dynamics of the relativistic jet. And for that particular object, the claim is that there is something like a 10-degree, maybe 15-degree offset between the two. The error bars are not very well understood, especially for the jet angle. There is no error quoted in the literature. So I don't know whether that's a misaligned jet or not. We would like to, we expect it to be aligned, but there seems to be 15 degrees off. There's a second object, this H1743, which Steiner and Klinkoff have done, where again you can compare what the inclination of the jet is doing relative to other inclinations that you can estimate. And again, it looks like it's roughly okay, but it could be off by 10 degrees, 15 degrees. For our modeling, we assume that everything is aligned. The binary, the accretion disk, the black hole spin, the jet, we assume that they're all pointing in the same direction. That's kind of important for our modeling. So at the moment, it's still a bit of a weakness in what we do, that we cannot independently confirm this alignment. 2 tests we have done indicate that the misalignment is not more than 10 degrees, maybe not more than 15 degrees. We would like it to be 0 degrees. But there is no clear example where you can say it is definitely misaligned. I think that's the best we can say.
Okay, well, we'll have more questions at cookies. Let's thank you very much again.